Hello. So here we have a cube centered at the origin, and it has length of 4, width of 4, and height of 4. Therefore, the volume is 64. So, what we're going to do today is use integration to find the volume of our cube. So let's look at it in terms of infinitesimal lengths. We have dx, dy, and dz. Okay? Of course, these represent infinitesimal lengths. So let's say, of course, I can't draw infinitesimal lengths, but let's say if we multiply dx by dy by dz, we get a very small cube, okay, as we have here, dx, dy, dz. Now, if we add up all of these tiny cubes within our big cube, we're going to find the volume of our big cube, which is 64. Okay, and of course, the best way to do that is integration. So in this case, we're going to use a triple integral, okay? So all we're going to have is 3 integrals, okay? And we have dx, dy, dz, okay? And this, of course, we have limits of integration. So this integral represents dx, this one represents dy, this one represents dz. So the limits of integration, so x goes from 0 to 4, y goes from 0 to 4, and z goes from 0 to 4, because it's a cube. Okay, and we can also simplify this by having an infinitesimal volume, the volume of our small cube. So it's exactly the same thing, but we can write it as this. dv. Okay, dv, an infinitesimal volume. So all we do is find the infinitesimal volume of a small cube, and we simply add up all the tiny cubes in our large cube to find the volume. Okay? So let's do that. So let's first of all integrate. But what do we have here? There's actually a 1 here. Integrate 1 with respect to x. Okay, so therefore we're going to get 0 to 4, 0 to 4, okay, of x evaluated from 0 to 4 dy dz, like that. Okay, integral of 1 is x, with respect to x, of course. Okay, and that's, of course, just 4. So therefore we get the integral from 0 to 4 of 4 dy dz. Okay, now we simply integrate with respect to y. This is going to equal the integral from 0 to 4 of 4y evaluated from 0 to 4 dz. Okay, and that's of course equal to the integral of 0 to 4 of 16 dz. Alright, and the final step is to integrate 16 with respect to z. This is of course equal to 16z from 0 to 4. 16 times 4 is 64. Therefore, that proves the volume is 64. So we can use triple integrals, but we can also use find the volume of the cube using integration, but in a different sort of way. What we can do is, let's say we have, okay, so the face of our cube, what's the area? It's 16. So this, the area is 16, okay? Now, let's say we split the cube into very small slices, infinitesimal slices, okay? And each slice has a width, okay, of dy. It has a very small width. Okay, and all we do is we simply add up all of the volumes of these small slices, okay, until we complete the whole cube. Okay, and therefore that's going to find us the volume. So first of all, what's the volume of these small slices? Well, the area is 16, okay, and we multiply that by dy, okay? 16 times dy is going to give us the infinitesimal volume of our small slice, okay? And we can do this in any other coordinates. We can have 16 dx will equal the dv, 16 dz equals dv. It doesn't have to be an infinitesimal slice going this way. You can have infinitesimal slices going this way, okay? Or with z, it doesn't matter, okay? But as long as you slice up our cube, we can find the volume. So let's do that quickly. So all we're doing is we're integrating from 0 to 4, okay, of 16 dy. Okay, let's look at that. 16 dy gives us the volume of our infinitesimal cube. If we go all the way along the y-axis, we have 4 units, don't we? Okay, therefore, we integrate these small slices from 0 to 4. That's going to equal 16y 0 to 4, which is of course 64. Alright, so we can use the triple integral, and we can also use the slicing method, where we slice the cube into very small chunks, and we find the volume of that chunk, which is 16 dy equals dv, okay? And then we simply add them all up along the cube, okay? Using integration. So, yeah, that's a very simple problem, looking at the area of multivariable calculus.